Today we're going to introduce vectors, and we'll start with vectors in 2 dimensions. So what if I ask you to plot the point P, which is at -2, 5, and Q is at -6, 3. You might want to go ahead and plot those points, or you can look on the next page. And I've got them plotted for you already. So this is a vector. Notice there's an arrow on one end. So the notation for a vector is the 2 capital letters with an arrow above it. Point to this. Now notice I started at P and I went in the direction of Q and I ended at Q. So P is the first letter I write and then Q is the second letter. On the other hand, if I was going from Q to P, I would write QP. The arrow above always goes to the right. It doesn't matter where it's going in the picture. What I don't want you to think of is geometry when this notation represented a ray. An array has infinite length because it goes on forever and ever and ever. So this is not a ray, it's a vector. So it starts at P and it ends at Q. We refer to P as the initial point and Q as the terminal point. Just some terminology with vectors. Sometimes, instead of representing it with the initial point and the terminal point and the arrow above it, we'll represent it a different way. And we'll use a lowercase letter. Sometimes you'll see in some texts, I lost my other arrow here. In some texts you'll see it with a lowercase letter and an arrow above it, or just simply a bold lowercase letter. So all of these represent a vector. Now a vector has 2 numbers associated with it. It has a magnitude and it has a direction. So the magnitude of a vector means how long is the vector? What's the length? And that's easy enough to figure out. If you go back to our picture, we can figure out how far it is from P to Q. There's 2 different ways I can think of to get it, which most students would use. And the symbols we use for the magnitude of a vector or the length of a vector is we'll have 2 vertical bars around the vector, whether it's represented this way or it's represented this way. Sometimes in some texts you'll see just a single vertical line on each side. And you're probably thinking, well, how do I know that doesn't mean absolute value? Well, it depends on what's in here. If there's just a number in here or a value, like a variable, then this means absolute value. But if there's a vector inside of here, then it means magnitude. So that shouldn't be confusing based on the context of your problem. All right, so let's go back with that vector v that we were looking at, and let's find the magnitude of that. So first, let me rewrite the coordinates for v. Let's see, P was -2, 5. And Q was -6, 3. Okay, so how do we get the magnitude or the length of a vector? Well, you probably think I could use the distance formula. So I use the double bars, my vector v, or if you wanted to write PQ, and simply use the distance formula between 2 points. And remember, that looked like this. We subtract the x values and square it, plus, and then we'll subtract the y values and square that. So the x values, we have a -2 minus a -6, and then for the y values, 5 minus 3. And if we simplify that, we're going to get 4 squared, which is 16, plus 2 squared is 4, and so we get the square root of 20. Of course, we should simplify the radical. So that's 4 times 5. The square root of 4 is 2. That comes out. And there you have it. So the magnitude of vector v is 2√5. Okay, what if we wanted the slope of v? Well, for the slope, we'll use our slope calculation between 2 points. And so the slope is going to be the difference of the y values, so 5 minus 3, over the difference of the x values, negative 2 minus negative 6. So we get 2 over 4, or 1/2. Easy enough. Now, instead of using the distance formula from the picture, we could have always done the Pythagorean theorem, which is where the distance formula comes from. This has a vertical change of 2. This has a horizontal change of 4. Hence, that's where we had the 2 squared plus 4 squared, and then took the square root of that. Let's get rid of that. All right, so what does it mean for two vectors to be equal? If two vectors are equal, both of those numbers associated with it have to match. So they have to have the same magnitude or the same length. They also have to be going in the same direction, which would mean their slopes should be the same. So let's plot, we already have the vector PQ. Let's plot another vector on that same graph, MN. This time M is going to be at the origin, and N is going to be at negative 4, negative 2. And so there's that vector from M to N. Notice it's the initial point is M and the terminal point is N. And that seems to match this vector PQ. They have the same length and they're going in the same direction. So those two vectors are going to be equal. It's useful because there's an infinite number of vectors in the plane that are going to be equal to each other. So, and by the way, you would just say yes, same magnitude, and you would actually calculate the magnitude of the two vectors that were given to you. We've already done that. That was 2 root 5. And same direction. And we could just use our slope calculation for that. They're both pointing in the same direction, and we had a slope of 1/2. Now, if they weren't pointing, excuse me, in the same direction, for example, if that second vector started at N and was going towards M, so if our arrow was on the other side, here instead of here, then we'd say those vectors are not equal. They have the same magnitude, but they're going in opposite directions. So that's important as well. So you can't just look at the slope and say, oh, the slopes are the same. You have to look at which side the arrow is on as well. All right, so the component form of a vector is an easy way, so we could compare a whole bunch of vectors and decide if they're equal. So for these two vectors that we were dealing with, the component form is going to be negative 4, comma, negative 2. So we use almost like a less than greater than symbol here. So this tells us that it's a vector. And the negative 4 represents the change in x from the initial point to the terminal point. And the negative 2 represents the change in y from the initial point to the terminal point. So if we go back to our picture, and we have these, and I draw another arrow just to highlight this. So to go from P to Q, we had to go negative 4 in the x direction and negative 2 in the y direction. Same thing from M to N. Negative 4 in the x direction, negative 2 in the y direction. So that's our component form. Negative 4, comma, negative 2. Those. All right, the component form is also nice when we're doing some of our calculations. Let's look at an example. Let's write the component form of the vector W if it has the initial point 7, negative 1 and the terminal point 4, 5. You might want to hit pause, go ahead and write your answer and check. All right, so I want to figure out W, and that's going to equal, so let's look at the x values first. I started at 7 and I wound up at 4 in the x direction. So I went down 3 units, or left 3 units in the x direction. So that component is going to be a negative 3. And then look at the y numbers. I was at -1, and I went to +5 in the y direction, so that's going upward 6 units. So that would be a +6. So the component form is going to be -3, 6. So if I want to define how we come up with this component form, basically the idea is we're going to subtract the x values, comma, and then subtract the y values, but we're going to subtract from the terminal to the initial. So if you can just remember the phrase terminal minus initial, that should help you remember how to get the component form if I give you 2 points. One last thing, what if I asked you to find that? Remember what that means. What does that mean? That means what's the magnitude? Well now, since I know the component form of this, that makes it really easy. It's just going to be the square root. The difference in the x's is the x part of my component form, which was -3. So -3 squared. And then the difference in the y's, that was the y component in my component form. So I simply just had to do, using my 2 numbers from the component form, the x squared plus the y squared, take the square root of that. So that's going to give me the square root of 9 plus 36, square root of 45. I can break that down, and that simplifies to 3√5. A little less work than if I had given you the 2 points, the coordinates of the 2 points. All right, what else can we do with this? All right, let's say we have a vector u, which in component form is 3, 4. So what you'll do is you'll just start at the origin, and you're going to go 3 units in the x direction, 4 units in the y direction, and that'll be your terminal point. So I've got that graphed here. Draw an arrow. So I started at 0, 0, and I went 3 units this way, 4 units that way. I mean, there's a lot of vectors in the 2-dimensional plane that are equal to this vector. And I could have started it anywhere. But when we're just given the component form, we'll just use the vector that starts at 0, 0. All right, now with that, let's draw 2u. What do you think that would be? If we look at our graph, well, that's u, or 1u. So 2u is just going to be the same vector, twice as long, going in the same direction. What if I asked you to draw negative u, or the opposite of u? And if you think of negative as the opposite, then that's pretty easy. There's u, there's the opposite of u. Now, what would the component forms be of these 2 different vectors? The vector 2u and the vector -u. So for 2u, well, we don't even actually need to graph. It's just going to be 2 times the vector 3, 4. So in component form, we can just go ahead and multiply a scalar, they call that, a number, times the vector, and we're just going to get a bigger vector, 6, 8. So that's the component form of 2u. How about -u? Same idea. Think of it as -1 times the vector 3, 4. And obviously we're going to get, as we saw in the picture, -3, -4. So having it in component form allows us to do some operations, and we don't even need to look at the graph, which is quite handy. All right, let's say we have another vector v, and v is at -2, 1. And I want to draw u plus v. So we're going to use that same vector u that we had in the last example, 3, 4. And on the same graph, I want to draw -2, 1. And then I want to draw u plus v. So let's get the visual for this. There's u, there's v. So what's u plus v? What does it mean to add vectors? Well, adding vectors means we're going to take, the first vector was u, so we have the starting point. Let me draw another arrow here. So we're going to start here, we're going to go to the end of u, and then from that spot we're going to add v. So we're going to put the initial point of v right here, and then take it to wherever that goes. So what that means is basically we're taking this vector and we're putting it onto there. So then u plus v equals that vector. It's where we started initially to where we ended up at the end, after traveling along the direction of those two vectors. So that's what it means to add vectors. Let me make a copy of this. Let's see if I don't have a copy. Let me make a copy of this. Let me put it here. And then let me make a copy of this one. Notice that the two vectors u and v, they determine a unique parallelogram for those two vectors. So when I give you two vectors like u and v, there's a parallelogram that they determine, and it turns out that the vector u plus v is the diagonal of that parallelogram. You're probably wondering, what about the other diagonal? We'll get to that shortly. Oh, I'm sorry, by the way, let's also do, so we did u plus v, let's go down here. What would v plus u equal? Well, let me get these out of the way. Instead, if I said u plus v, v plus u, that means that I'm going to start at v. So I'm starting here, I'm traveling to this point, and then from there, I'm going to follow vector u. So I'm going to take u and put that onto there. And where do I wind up? The same vector that we had before. So that shows us that vector addition is commutative. All right. And so that parallelogram law, the two vectors will determine a parallelogram, and the sum of the vectors equals the diagonal of that parallelogram, if they're both starting from the same point. Now, what if we didn't want a graph? Well, to add two vectors, if they're in component form, it's so easy. All you have to do is add the x components and add the y components. And if we're multiplying a vector times a constant or a scalar, a number, we're basically going to distribute and multiply that number times each of the components themselves. So that makes life a lot easier. So let's go back up and do that u plus v again. So, and let me do it in a different color. Let's go green. So the vector u, let's see, the coordinates for u was 3, 4, the components. So when I said what's u plus v, all I have to do is -2 plus 3, or 3 plus -2, and 1 plus 4, or 4 plus 1. And so that gives me the vector 1, 5. And from our picture, that is, let's get these out of the way. That's vector 1, 5, because we go 1 to the right and 5 units up. All right, what, on the other hand, would happen, do you think, if I asked you to draw u minus v? What would that mean? How am I going to do u minus v? Well, if you think of that as u plus the opposite of v, we go over to our picture. So u plus v would look like that. Well, what's the opposite of v? The opposite of v is going to be a vector of the same length, but it goes in the opposite direction. Let's go with purple. So it's going to go like this. And if I start that at the origin, that would be the opposite of v. So when I ask what's u minus v, and you think of that as u plus the opposite of v, that simply means we'll start at the initial point of view, go to its terminal point, and from there we're going to add on to that the opposite of v vector, which is going to go that way. So, boom, right there. And so what's my answer? What's the resultant vector then started here and wound up here? That's going to be u minus v. Well, let's go back to that parallelogram that we were talking about. Here's the parallelogram that these two vectors create. This vector u minus v, if I just move it in the plane, it's still the same length. It's still going in the same direction. Let me slide it over into my parallelogram, and lo and behold, what do we have? We have the other diagonal of that parallelogram. So u plus v gives you one diagonal, u minus v gives you the other diagonal.